We'll continue our class. So each deadlock avoidance, you can use one of these mutual exclusion or resource holding. You release no preemption or in a circular way. So this, how do you modeling a deadlocks? So the four conditions can be modeled using a directed graph. This is the graph, this directed graph, meaning that process are represented by circles. This is a process. And resources are represented by squares. Resources. So P1 is if you this is a directed graph, meaning that is a direction. You have a direction. The line have a direction. Is a directional one way. So R1 is serving a P1. Resources now at current resources is held by P1. So P1 is holding R1. No one cannot use R1 except for P1. So P1 is waiting for R1. This one is a B. P1 is waiting for R1. A cycle in the graph means that there is a deadlock. If there's a cycle or loop, some call it cycle, some call it loop. Loop meaning that you are like stuck in the loop. Waiting, you request waiting, request waiting, request waiting. So you stuck in the loop. This is a deadlock. So R1 printer, R2 RT plotter, okay. P1, P2, 3 resources. So as a P1 request, I look at the printer R1. P1 release R1. So this is scenario 1, okay. P1 request and allocate the printer P1. And this one is R1. Sorry, P1 is supposed to be resources. Process supposed to be circle P1. It doesn't matter, but this textbook use circle. So R1 is the resources. For P1 request R1 and it is allocated. And then to P1 release, so finish, so it's free now. P1 and R1 free. P2 request, so you have P2 here, and this is R2. So you request and it is allocated. And then P2 release R2, so it is free. And P3 request and is created the plotter R3. So this is P3 and this is R3. So request, allocated, finish. So it is free. So P3, this is scenario 1. There are no cycles in the directed graph. Conclusion, deadlock can occur even if each process requests every resource if the resources are released before the next process. So the keyword is if release. If not the keywords, key sentences. If the resources are released before the next process. Resources are released before the next process. So R1, P1, R1, so when it's already done, deallocate, so free. R2 is serving P2. After it finish, so it is free. R3 serving P3 till finish, so it's free. So this is the perfect situation. No deadlocks. Resources are released before the next process request them, okay. It is released. It is free because it is released before any other jobs want to request that resources. Scenario 2. So P1 request allocate R1, P2 request allocate R2, P3 request and allocate R3. At the same time, P1 request R2, P2 request R3, and P3 request R1. I know this is the deadlock situation. So you have here this is the circle. So R1, this is the previous this is scenario 1 to 3. R1 serving P1, R2 serving P2, RT serving P3. And suddenly P1, okay, I need to access R2, block. P2 needs to access RT, block. And P3 need to access R1, block. You can see this is kind of a cycle. This is kind of a cycle. It's not a perfect cycle, but this is a cycle. So this is a loop. And this is a deadlock. Again, this is a sticky situation. So because deadlock, because every process is waiting for a resource held by another process, but none will be released without operator intervention, control alternate, delete, restart, or whatever, and thus certain processes. So scenario 3, you have scenario 1 and 2. So now P1 request and allocated R1. P1 request and is allocated R2. P2 request R1. P3 request and is allocated R3. So this, okay, it's better because this is like more action needed. So you have here, we have to see, P1 request and is allocated R1. So P1 request, so R1 currently serving P1. And P1 requests and is allocated R2, meaning that resource 1 and resource 2 is held by P1, serving P1. P2 requests R1, so P2 requests R1, so now because R1 is serving P1, so this is block. Sorry for that. P3 requests and is allocated R3. So now R3 is serving P3. Where are we now? 4, now 5. P1 release R1, which is allocated to P2. So R1, okay, P1 already finished the process. So he doesn't need the R1 anymore, so it's free. So now R2, so now R1 is serving R2. Before this is a block when this one already free. So R1 is serving P2. P3 request R2. P1 which P3 request R2. We have a P3 request R2. Where is it? P3 request R2. It's supposed to be, okay, this is a red. P3 request R2. Okay, but it's a block. It is blocked because R2 now is serving P1. Okay, P1 which is P3 request R2. So now this is a P3 request R2. Not sure why it doesn't have an arrow here. P1 release R2, which is allocated to P3. So okay, after okay, now P1 already finished using finished his processes. So he doesn't need R2 anymore. So he released this. So now P3 instead of block, so now it is allocated. P3 now being allocated R2 resources. R2 is serving the P3. So the graph can be expanded to include several resources of the same type that can be allocated individually or in groups to the same process. Okay. So you can classify, you can break, you can put several resources into the same type. Device of the same types. I mean, you have a printer, what else? Scanner. You know, usually it's 3-in-1 now, but let's say it's 10 years ago, you have a printer, single device, scanner, single device, copier, single device. So you can put this. You can put all these devices into one entity. Device of the same type are classified into one entity. The arrows show the links between a single resource and the process using it. Single resource and the process using it. So A is stable, okay? A is stable, but when all three processes request more than one resources, so this one A is stable. But when all three processes request one more resource without releasing the one they are using, a deadlock occurs, okay? let's say this one is on the P1, this one is R1, and this one is R2, and this one is R3. Okay. At the same time, P2 need to access R1, P1 need to access R2, P2 needs to access R3, and P3 might need R1. So no one are releasing their resources. Okay, no one released their resources yet. So this is the deadlock situation. This is a stable situation, stable condition. Sorry, stable condition. This is a deadlock condition. Okay. Requests and releases are unpredictable, and that makes it difficult to design foolproof preventive policy. So this is a dynamic. It's interactive. Okay, it's really unpredictable. So you cannot have a system, or you cannot have a perfect design. Okay, if you do it like more locking, more this and that, you will increase the deadlock. But if you make it too relaxed, it will suffer. Data integrity will suffer. So you must have a trade-off. Okay, must balance. Everything must be in balance. So that's why they don't have a foolproof preventive policy. Okay, foolproof preventive policy. Maybe some other conditions, maybe some other algorithm is okay for this kind of situation, but it's not okay for different situation. So there is no one size fits all. So no one size fits all. 3 strategies to deal with the deadlocks: prevention. Okay, this, as the name suggests, avoidance and detection. Prevent one of 4 conditions occurring. Avoid the deadlock if it becomes probable. Detection, detect the deadlock when it occurs and recover from it gracefully. So the OS must eliminate one of the 4 necessary conditions to prevent deadlock: the mutual exclusion, resource holding, okay, mutual exclusion, resource holding, no preemptive, and circular. Okay, these 4 conditions. Eliminate these 4 conditions to prevent deadlock, which is not easy. It's complicated. Mutual exclusion is necessary because certain resources must be allocated to one user. Remember the example I give earlier. When you have a 2 process X, read X, write X equal to X plus 10, and this is process 1, this is process 2, read X equal to X plus 10. So this X is a shared variable. So maybe you want to mutual exclusion. You want to, okay, do the process 1 first, lock process 2 from accessing X. So P1 will read X. So X equal X plus 10. So now it will execute write X plus 10. So X is 20. Move to the process 2. So P2 will read X equal to 20, X plus 10, so 20 plus 10, 30. So this is the correct. So this is mutual exclusion. You cannot do so many mutual exclusion, or you cannot do less mutual exclusion. Some of it is very important, okay, to do mutual exclusion. But if too much mutual exclusion, your system will become very slow, and it's not really effective solution. Must be balanced. Okay. Resource holding can be avoided by forcing each job to request every resource it will need to run to completion when it. Okay, you cannot hold this resource. You cannot hold this resource even though it's idle. You cannot just hold this for these jobs to come in. Okay. You must force each job to request on demand. Okay. When you want to use it, you demand the resource. Not that it's specifically save it for you or reserve for you. You have to request it on demand. All right. And then no preemption could be bypassed by allowing the OS to deallocate resources from jobs. So you can have no preemption. So you have if you're using the OS, so OS has the power to deallocate resources from jobs because maybe some of the jobs are coming in and it is more priority, more important than your jobs here. And circular weight can be bypassed if the OS prevents the formation of a circle. Solution is based on a numbering system for resources. Okay. Solution is based on numbering system for resources. A printer one, this number 2 and tape number 3 and plotter number 4. Let's say if a job needs a printer and a plotter, it will request for printer first. Okay, based on the priority. Okay, let's say printer, you need a printer and a plotter. So it will request a printer first. It will request a printer first and then maybe a plotter. Let's say it needs a printer and plotter. So based on the priority, printer first and the plotter second. Even if not just to use the plotter first followed by a printer, it still has to request to the printer first and use it later. Alright. The job has to anticipate the order in which it will request for resources. So even if the jobs, let's say I need a plotter first followed by a printer, but it still need to request a printer first, then a plotter. This is to avoid a circle. A job has to anticipate the order. It has to anticipate the order in which it will request for resources. So jobs must request for resources in ascending order. In order is easy. I mean, in a nutshell, is in order. You have to follow the chain line of command. Printer 1, this 2, tape 3, plotter 4. You cannot override plotter number 1, printer number 2. No. If you already like decide the priority, you have to follow the order. So the OS also can avoid deadlock if it is known in advance the sequence of requests with each active process. It can avoid deadlock if it knows in advance the sequence. So this is the best if you know in advance, but not all systems are like that. So one of it is the banker's algorithm proposed by Dijkstra, regulates resource allocation to avoid deadlocks. So this Dijkstra is the person that inventing the shortest path, which is now used. I mean, it's a basic for all these Google Maps or Waze. Dijkstra, very brilliant mathematicians or physicists. Because last time there are no like because this is in 1950, 1960, there are no like science computer course. It's always either mathematics or physics. So he's a brilliant physicist and also a brilliant mathematician. So he created a banker's algorithm to regulate resource allocation to solve this problem. So the algorithm is based on a bank with a fixed amount of capital. Okay. Fixed amount of capital that operates under following principle. Maybe the bank has 10,000. The bank only has 10,000. Of course, it's a very poor bank, but this is just an example. Banks have billions, billions, whatever. But let's say for a small example, no customer will be granted a loan exceeding the bank's total capital. Huh? Yes? Any questions? Noise. It's making that sound. Okay, over you, all of you. Okay. Right. Okay, thanks. Okay. Right, we will. No one. Okay, you have a 10,000 ringgit. No customer will grant a loan as the bank's total. If any customer wants to do a personal loans, ask for 20,000, so straight away the bank will reject it. Okay, it's a common sense to do. It's a logical things to do. All customer will be given a maximum credit limit when opening an account. Okay, you have a 2,000, but you can use your credit limit up until 3 to 4,000. This is normal for business account. No customer will be allowed to borrow over the limit. If you are, if you, if your maximum credit is 5,000, it will be 5,000. You cannot allowed to borrow over the limit. The sum of all loans won't exceed the bank's total capital. Multiple users wants to borrow the money, so it cannot exceed the shilling. We call it a shilling of 10,000. So this is the case number one, case one. So we have a loan amount. Okay, C1 customer loan amount. So C1 doesn't need a loan, has his savings. So maximum credit is 4,000. So remaining credit is 4,000. So C2 has a loan amount. He wants to make a loan, 2,000 ringgits. Maximum credit that bank gave him, give to him is 5,000. So 5 minus 2, 3,000. You have remaining credit. And C3 is 4,000 loan amount, maximum credit 8,000. Of course, if you loan this is a conventional practice of bank. If you loan more money from the banks, they will allow you to maximum credit. Okay, if you don't use wisely, you're gonna be in trouble. I hope when you graduate, you know how to manage your financial. That is very important nowadays. Manage your financial. Okay. Don't go buy expensive stuff. Live within your means. Okay, we continue. So remaining credit is 4,000. So the loan is 2 plus 4, 6,000. The total capital fund 10,000. So banks still have 4,000 extra to play with. So 4,000 can at least the banks can at least the minimal condition. Banks can satisfy the requirement of remaining credit one of the customer. So at least like customer 1, 4,000, 3,000, 4,000. So all the remaining credit from the customer is less than the balance of the is less or same with the balance of the bank. So bank can satisfy if, let's say, remaining a user C1 wants to, I have a very important order, but I need 4,000. So bank can satisfy that requirement. So this bank is in a safe state. Okay, still have 4,000. So the bank still has enough money. So this is a safe state because the bank still has enough money to left to satisfy the maximum request of C1, C2, and C3. Not all C1, C2, and C3. At least one C1, C2, and C3. Okay. Now this case number 2. Okay, business is expanding, growing, and stuff. So C1, in order to expand his business, he needs to make a loan. Before this, no loan, using all his savings. No, business is expanding, his economy is good, whatever. So he wants to do a loan amount to 2,000. So maximum credit 4,000. So he has remaining credits of 2,000. So loan amount C2 wants to add another 1,000. Okay. I want to expand. I want to buy this machine whatsoever. It cost me 1,000. Loan from the bank. And then the remaining credit is 2,000. And C3 also, the loan amount stays here. Okay, that's why I loan more at the initial phase or at the beginning, so that I don't have to loan from the bank after that. Okay, so C3 remains static. So total loan now is 9,000 by adding 2,000 and 1,000 here, so 9,000. total capital fund is 10,000. So you have bank only have 1,000 ringgits to play with. So 1,000 ringgit cannot even satisfy any of the remaining remaining credit. Okay, so this bank is an unsafe state because only 1,000 is left and the banks cannot satisfy anyone maximum request. Let's say if the bank lends 1,000 to anyone, it will be a deadlock. Let's say, okay, C1 need another 1,000. So 1,000 if loan to the C1. Okay, so now at the moment, okay, C1 wants to loan, C1 wants to loan 1,000. Okay, instead of 2,000 become 3,000. Now the loan, the bank only have 0, which is a very bad management of the bank. The bank should not have 0 in his account. Okay, but this is just an example to show you. It will be a deadlock. Okay, the bank cannot make a loan. So the bank cannot satisfy, cannot give loan to anyone. And unsafe state does not necessarily lead to deadlock. So this 1,000 is not a deadlock yet. Okay, 1,000. So bank has 0. Bank has 0 fund now at his current account. But this is not a deadlock yet. But it is a potential. Sure to be deadlock. Okay, sure to be deadlock in the future or next few days.
Doctor.
Yes.
How do we decide if it's in an unsafe state?
So this is the situation with the unsafe state. Okay, you have 1,000 here, and the remaining credit here, based on the jigsaw algorithm, it cannot satisfy the remaining credit of any of the users. So this is unsafe state. But this is not a deadlock yet. This is unsafe state, which is a logical things. Okay, you have 1,000. Bank only have 1,000. It cannot serve. Let's say C1. Okay, I need to use the whole of my remaining credit. The bank cannot satisfy that because bank only have 1,000. This situation, bank have 4,000. Okay, not all the users, but at least single users. So bank can, let's say C1 have, okay, I need to use my remaining credit. I want to expand my business or something else. He want to buy in bulk, so he need 4,000. So he can satisfy C1. He can also bank can also satisfy C2 and C3. Not all of it in one time, but at least one user. So 4,000. This is a safe state. Okay, 4,000 equal or more than the remaining credit. Look at this situation, 1,000. Let's say C1 I want to use the all remaining credit. No, I only have 1,000. Bank said, you cannot have your remaining credit. Maybe next month or next 2 months. Okay, when I have my payment back from other borrowers, something like that. So this is unsafe state, and unsafe state is not a deadlock yet. Okay, but it's a potential sure to be a deadlock after this. Okay, sure potential. It's a potential. Yeah.
So if, like, say, in this scenario, if the total capital fund left is like 2,000, is it still considered safe or is it unsafe?
If it is a 2,000, it can satisfy at least a single user, C1 and C2. So it still is a safe state, but safe state is on the borderline. You know what I mean? On the borderline state, something like that. Okay. Just
thank you.
Okay. At least a single user the bank can, but this one not. The bank cannot satisfy any users the remaining credit. So this unsafe state is not a deadlock yet, but it's sure to be deadlock. It's a potential to be a deadlock. Okay. The bank should not operate like this. So as long as the bank's capital is less than the maximum amount available for individual loan, it cannot guarantee that it will be able to fill every loan request, right? So this banker's algorithm. a famous algorithm for a resource, we call that how to manage your resources, bankers algorithm. Another thing is to note is the customers are not required to request for a maximum loan, but the bank doesn't know the exact amount that will eventually be requested. Okay, customer doesn't really need remaining credit 2,000, maybe enough for this, but bank doesn't really actually knows what customer wants next or in the future, or what eventually customer will request. It just have 1,000. Okay, the memory left is maybe the CPU usage only left 10%. Okay, but the CPU doesn't know how many it cannot know beforehand how many resources that the jobs need. Okay, the jobs can request maybe 20% of the CPU, so CPU cannot satisfy that, because CPU only left 10%, and if job requests 20% of the CPU, sorry, I cannot entertain you because I have 10% left, so you have to wait. So these are banks, what you call it? What? I forgot already. Bankers algorithm. Sorry, bankers algorithm. You call it. So you can replace this loan amount to the device allocated. Okay. Loan amount you can replace with the device allocated. Maximum credit you can maximum required, and then remaining credit remaining needs. So you can, so in a safe state, okay, in a safe state, at least one job can finish. Safe state, at least one job can finish. All right. So total number of devices allocated is 6. This same with the case 1 of bankers algorithm. Number of devices in the system 10. So safe state 6. 4 are still available. Safe state. So 4 can request job number 1, job number 2, or job number 3, provided they don't request it at the same time. So this same with the case 2 of bankers algorithm. So only one device cannot satisfy job number 1, job number 2, or job number 4, because they only have one device left. Okay, this is an unsafe state. Again, unsafe state is not a deadlock situation, but it's a potential OS. Intelligent OS must realize this. Okay, we are now into the unsafe state. We must do something. Okay, all right. Unsafe state is not a deadlock yet, but it's a potential to be a deadlock. So the OS must be sure never to satisfy requests that move it from a safe state to unsafe state. So the good OS must know this, must able to sense this. Okay, must be sure never to satisfy a request that moves it from safe state to unsafe state. When a request is received, the OS must identify the job with the smallest number of remaining resources. So identify the job with the smallest number of remaining resources, and make sure that the number of available resources is at least equal to the number needed for this job to run completion. Okay, meaning that this one, 4 is equal to the remaining jobs. He wants to, the device want to satisfy the job requirements. Make sure that the number of available resources is at least equal, keyword equal, to the number needed for this job to run to completion. Again, this bankers algorithm is created like 1950. So it's like around 60 years ago. Of course, at that time it was brilliant, but it's also from this we can learn it's not a practical. Okay, as a job enters the system, it must predict the maximum number of resources. As a job enters the system, you might never know. Maybe your files may be added like a lot. Maybe your program, I mean, if you coding, when you add the data structure, or you want to do a simulation, you don't know, maybe your simulation in the future, when you add some command, when you add some lines to do jobs, maybe it become bigger and bigger. So you can never know what is the maximum number of resources you need. Not practical for interactive systems. The number of total resources must remain constant. If a device breaks, let's say you have two SSD drive, and then one SSD drive breaks, so the algo won't work on this type. It doesn't have a foolproof or fault tolerance. We call that a fault tolerance. It doesn't have a fault tolerance to deal with this if device breaks. The number of jobs must remain fixed. Not possible in the interactive. This interactive system is on demand. You can add it or you can deallocate or something. It cannot remain fixed. Of course, it is certain job situation you must remain at a fixed. Fixed allocation. But it's not a good way to manage jobs or OS. So the overhead cost of running avoidance algo can be quite high. Okay, of course you can just let it run, but if you want to avoid a deadlock or starvation, it can be this overhead. Okay, this is your normal code. If you do a programming normal coding, maybe you have 20 lines, but if you want to add the avoidance algorithm, maybe it becomes like 50 lines or something, more than 20 lines. So this is an overhead. This overhead will increase processing load, will increase heat, whatever your OS. Your OS has to work more. It has to be in for each. There are many active jobs and many devices, because it has to be invoked for each request. Resources are not well utilized because the algo assumes the worst case, hence keeps vital resources unavailable to avoid unsafe states. So, if you assume the OS always assume the worst case, it's not a good system, okay? Because it will keep the vital resources, the most priority one, unavailable. No, you cannot use this unless it's very important, because the OS want to avoid the unsafe states. Scheduling suffers due to poor utilizations. Okay, if you just keep some resources unavailable, it's wasted. So scheduling suffers due to poor utilization, and jobs are kept waiting for resource allocation. Keep waiting and waiting. May lead to indefinite postponement of a more complex job requiring many resources. So it can lead to indefinite postponement, postpone, waiting, job cannot run, of a more complex job requiring many resources. Of course, you can just restart, Control Alternate Delete, and task, something like that. But it's not. It is effective, but is it a good way to do that? No, it's not really a good way, but it works every time. So detection, deadlock can be detected by building directed resource graph. Again, resource graph. You mean a resource graph? You build a node, and then you put a line, whether it's you have an arrow here, it's a directional, or just this a graph. If no arrow, meaning that it's a bidirectional. This just a graph theory. The way you visualize a node or whatsoever, it can be engineering, it can be a protein based. If you learn chemistry, in a protein or organic chemistry, or in like Waze or Google Map, it's like node is a source to destination, something like that. It's a graph theory, just a way for you to visualize a situation. And looking for cycles. If it's a cycles, it is not good. Okay, it's a loop. If you detect a cycle as a loop, going in loop, meaning that you are in deadlocks. The detection algo can be executed when appropriate, every hour, once a day, when there is noticeable throughput degradation. Okay, your OS, good OS, we have data analytics. Okay, day by day. Okay, when you run the simulation, when you run a video rendering will take a lot of resources. Okay, your system will become slow. Maybe when you do like me, like video rendering, I can check. For your classes, when you do video rendering, try to break it up into smaller. Takes a lot of. You need a really powerful PC with a GPU. You want to buy a new PC, buy with a GPU and RAM at least 16 gigabyte. Okay, the detection algo reduce a directed graph. So if you do algo, you reduce a directed graph, meaning that more resource will become free. Or you detect this, so you do something, so you can free. You can free the allocation. You can deallocate. You can free the resources quickly or in the most effective manners. So steps to reduce graph: find a process that is currently using a resource and not waiting for one. Find a process currently using a resource and not waiting for one. Remove the process from the graph by disconnecting the link tying the resource to the process. Disconnecting the link tying the resource to the process. The resource is returned to the available list. Of course, you cannot just simply disconnect the link tying. If you do a video rendering, if you disconnect that or you stop that, you have to do it all over again. Only on the jobs that can be resumed later, where you can, this is the whole process, maybe this jobs coming in, so you can stop here, you mark here, this is where the job stops. So you do other process as well, most priority, then you come back here, you continue. So if this this jobs is not really priority but is use a lot of resources, you can just stop, pause, you mark terrible mark. You mark where you stop the jobs current, then you go do something else, then you come back, you continue where it stops, in the point that where you stop, you continue from there. Cannot just simply disconnecting the link. Find a process that is waiting for resource class that are not fully allocated. So process that is waiting for resource classes that are not fully allocated. This process does not contribute to the deadlock, since it will eventually get the resource it's waiting for, finishes and return the resource to the available list. It's a logical things to do. Not fully allocated, it's like the smallest job or something, that low hanging fruit. You can give this job because it's not affecting anyone. You can just give these jobs go first, execute first, finish, clear the resources. Go back to step 1 and continue with steps 1 and 2 until all lines connecting resources to process have been removed. So the goal is like this nodes. So you have here, then maybe you have here. The goal is to remove all lines connecting, to release the resources, to freeing the resources. In A, this go to A. This circle is what? Circle is process. Circle is process. Rectangle or square is resources. You have P and R. P process, R resources. So now P1, R1 resources 1 is serving a P1. Resources 2 serving a P2. Resources 3 serving a P3. And at the same time, P1 wants to access R2, but now R2 is serving P2, so block. P2 tried to access R3, but now R3 currently serving P3, so this is also block. All right. So now, okay, B. Okay, we have a situation, okay, B. Now, at the moment, after sometimes R3, P3 already finished using, finish its jobs. So it doesn't need the R3 anymore. So it will release this one, and R3 will be allocated to P2. Now P2, we call that P2. P2 already finished using R2 and R3. Okay, P2 already finished using R2 and R3. Since P1 request for R2, so R2 now will be allocated to P1. Before this, it is blocked. So now R2 is what? Serving P1 with R1. And D is after P1 finish the jobs, he doesn't. Okay, I already finished the jobs. Terminated it, and it will free the resources of R1 and R2, and this is the everyone happy. Okay, all are free, everyone happy. Can do a perfect square, sorry. So this D is when the resource already all being freed. If there are any lines left, this indicates that the request of the process cannot be satisfied and that a deadlock exists. If there are any lines left, this indicates that the request of the process cannot be satisfied and the deadlock exists. The flowing graph shows a deadlock situation. So you have here, okay, P1, this I think this is self-explainable, same like P2 tried to access R1 but now it's serving P1, so okay, P2 tried to access R3 but now it's serving P3, and P1 tried to access R2 but now R2 serving P2. Okay, now P3 already being released, and now R3 is allocated to P2. Now it's serving P2. But still R1, P1 doesn't release R1 yet because still has to finish its jobs. And R2 also still using is still used by P2, and P2 doesn't release the line yet, doesn't release the resources R2 yet. So this is blocked, still blocked. And this, when this happens, you have a loop here. You have a loop, or something like that. Loop. It doesn't matter how you draw it. It's a loop. So when it's a loop, it's a deadlock. You want to avoid this. Once a deadlock is detected, it must be untangled and the system return to normal as soon as possible. Recovery algorithms require at least one victim and expendable. So you have in your team members, those with the weakest link, those will become a victims. Okay, like you have a company with 5 workers, and then maybe business not growing so well. You have to sack 1 people, so you have to find a victim. We call that it is expendable, which is very, but sometimes you have to do that. In certain circumstances or difficult situation, you have to do that. You must be a bad guy. Removing the victim, but of course you cannot simply removing. You have to select one of the, the expendable. Those are expendable. Those are the weakest link. Removing the victim from the deadlock will free the system. Okay. The job that becomes a victim has to be restarted from the beginning or from a convenient midpoint. Okay, the jobs, maybe if like you do certain, like I say, video rendering, you cannot stop. You have to finish it. If you stop it, you have to restart. You have to start all over again. I'm not sure if any software that can do that. I'm not very good in the multimedia, but I think you cannot do that. And then maybe some of like downloading a file from torrent or download, you can stop at a certain point. Okay, stop at 52%. Maybe you can continue later. Okay, something like that. We just have a couple of slides to finish. Just bear with me. As simplest and most drastic approach to terminate all active jobs and restart them. Method 2, terminate only jobs involved in a deadlock and task the user to resubmit them. Okay, you can do a control delete and task certain jobs if your computer becomes slow. Method 3, to identify jobs involved in a deadlock and terminate them one at a time. And then checking to see if the deadlock is eliminated after each removal. Okay. So first, simplest, I'm going to find a victim. Simplest, most relatable is terminate all active jobs and restart them. Close, restart the PC, push a shutdown button, something like that. Simplest. Method 2, terminate only jobs involved in deadlock and ask the user to resubmit them. When you see, sometimes you see a pop-up, okay, it's unresponsive. You control the delete, you delete that, so you remove the deadlock. Method 3, identify jobs involved in deadlock. Maybe I think this program taking along or taking more resources, so you terminate them. So method 4 can only be used of the job. E of the jobs keeps a record, snapshot of its progress, so it can be interrupted and continue without restarting from the beginning. This is the best. The snapshot is like the landing in the staircase. Instead of forcing a ascender-descender to return to the bottom of the staircase, he only retreats to the nearest landing and wait for others to pass. Okay, maybe certain stair you have, you only retreat to the nearest landing, okay? Instead of going down, all the way down, go to the nearest landing point and wait for others to pass. Become a man, become a good man, and then okay, sorry. Method 5 selects a non-deadlock job, preempts and resources holding, and allocates them to deadlock process so it can resume execution, thus breaking the deadlock. Okay. Non-deadlock job preempts the resource if it's holding and allocate them to the deadlock process so it can resume, thus breaking the deadlock. So method 6 stops new jobs from entering. Okay. It's them to allow non-deadlock jobs to get resources, they need to run a completion. So factors to consider when selecting a victim with at least negative effect on the system. Priority of job. So of course, the high priority jobs are usually untouched. CPU time used by a job. Jobs close to completion are left alone. I need just a little more, just a little bit time, like this one, just to finish the lecture slide. Okay. The number of other jobs that would be affected if these jobs were selected as the victim. Okay. Number that would be affected. So like if you really say this HR is a company, you really set an important person, a system engineer or programmer, without having without replacing equivalence to, I mean, without replacing sometime someone that is really high skilled to do their jobs. Your system will be it will your all other departments, the company will become very messy and uncontrollable. Okay, so choose your victim wisely. Choose your victim wisely. Okay, starvation, the last one, is the result of conservative allocation of resources where a single job is prevented from execution. Okay, this starvation is worse than a deadlock because you keep waiting for resource that never becomes available. Okay, the dining philosophers again from Dijkstra, this is a Dutch guy, okay, very brilliant mathematician and physicist. So he introduced a dining philosophers. So the philosophers sit around a table, each deep in the thought. All these philosophers. In the center is a bowl of spaghetti. There are forks between each philosophers, okay? So there are forks between each philosophers. The philosopher must use 2 forks on either side. So in order for the philosophers to eat, must use on either side, because you have 5 philosophers. The ideal number of forks is 10, but now you only have 1, 2, 3, 4, 5, and you must use both forks to eat the spaghetti. By the way, it's not look very, talking about foods, because this is the last, I think, for Muslim, this is the last day for you to eat before tomorrow you have to start fasting. Okay. Just bear with me before you want to have your lunch. Just this final slide. So the philosopher must use two forks on either side. So a philosopher can only eat or think at a given time, but cannot do both. So philosopher can only philosopher need to think or eat, but you cannot do both. Okay. If you don't eat, you think. If you eat, you cannot do anything. You cannot think anything. You just eat. Don't think. All right. A philosopher can only eat, think, will eat or think at a given time, but not cannot do both. Okay. First, P1. Okay. First, P1 now wants to eat. So it will take F1 and F5. Okay. P1 is the first to start eating using the F1 and F5, and then P3 does likewise. P3 also eat, so it using F2 and F3. Okay. So now P4, P5, and P2 cannot eat. Although they are hungry, they cannot eat. Seems like you, although you are for lunch now, you cannot finish yet. Here's a little bit more. P2 decides to begin the meal. Okay, P2 decides to begin, but is unable to start because no forks are available. So P2, P4, and P5. P2 is hungry. I'm so hungry, but I cannot use the forks because now is F1 is P2 can only use F1 and F2, but F1 currently using by P1 and F2 currently using by P3. Okay, okay. Now, okay, like P3 finish eating. Okay, release the F2 and F3. Okay, without washing the fork. Okay, now P2 realize F2 is free, but not F1. Still, he cannot eat that because he has to use both on left and right. So P4 and P5 are still thinking. Okay, P4 and P5, maybe they have lunch earlier, so they're still thinking. P1 hasn't finished eating yet. P1 is eating a lot of it. Okay, P1 is eating and not thinking of others. P3 decided to eat again. Okay, P3, okay, I finished eating, but now I want to eat again. Still not enough. I think I eat too little. I want to eat again. So P3 use F2 and F3. P2 is like really hungry. His tummy already make a sound or something, but he still cannot eat the pasta. Okay. All right. And then P1 finish. Okay, I think I think I am full. So I release F1, but P2 still cannot eat because F2 is used by P3. So it can become so this scenario could continue forever. Okay, P2 cannot eat. P2 can call it starvation. P2 can die of starvation, or of course he went out and take out or something. Okay, resource required is never released. So in computer, final slide. In the computer environment, the resources are like forks. And the competing processes are like dining philosophers. Competing processes, jobs. And this one is resources. Process or jobs, process. If the resource manager does not watch starving processes and jobs and plan for their completion, they could remain in the system forever. So manager does not watch for starving processes. This process have it for very long times and does not plan anything for them. It could remain in the queue forever. Once the system is detected, the system can block new jobs until the jobs have been satisfied. Okay.